Welcome back to QHSE Talks. So I want you to picture this scenario for a second.
Okay, I'm picturing it.
Right, so it is 2 a.m, and you're inside this sprawling, 1 million square foot logistics warehouse.
Wow. Huge place.
Massive. And the facility is mostly quiet, right? Except for maybe the hum of the massive HVAC units up on the roof.
Yeah, standard off-hours vibe.
Exactly. But tucked away in this distant corner, deep inside a rack of cardboard inventory, a lithium-ion battery in a damaged pallet starts to experience thermal runaway.
Uh-oh, that's not good.
No, it's really not. So it gets hot, then it starts to off-gas, and this thin gray ribbon of smoke starts curling upward toward a steel ceiling that is, 40 feet high.
Right, and here's the really terrifying physics of that situation. The temperature down at the floor is rising, obviously, but up at that 40-foot ceiling, the air is still a cool 68 degrees.
Because it's so far away.
Exactly. The heat from that small battery fire is totally dissipating long before it ever reaches the top of the building. But the smoke, that toxic, really buoyant mix of particulate matter and carbon monoxide that is steadily climbing.
And it just starts banking against the metal roof.
Yeah, and slowly beginning to fill up that massive cavernous space.
See, this is the silent, invisible window where a fire is honestly the most lethal. And it's the exact window we are exploring in this session of QHSE Talks.
It's such a critical topic.
It really is. So if you are a safety professional, an engineer, a facility manager, or especially if you're a candidate currently prepping for your ASP or CSP exams, pull up a chair. Turn the volume up.
Because today is a very specific targeted session for you.
Yeah, this is a specialized exploration custom tailored for those exams. We are looking intensely at ASP Domain 4, Topic 6, which is all about understanding fire detection systems.
And, we are treating this with the gravity it really deserves. Fire prevention and protection is a massive pillar of safety engineering.
Definitely. Look at the exam blueprints.
Right, this specific domain makes up 12% of the ASP. And it's nearly 11% of the CSP.
That's a huge chunk of your score.
It is, but passing a multiple choice test is just like the administrative milestone here. The ultimate goal is actually executing the core duty of a safety professional.
Which is anticipating hazards before they manifest.
Exactly. It's about really understanding the intricate, elegant, and honestly sometimes super frustrating engineering that goes into protecting human life. Not to mention billions of dollars in property.
Yeah, so we aren't just going to sit here and memorize acronyms today. We really need to understand the why and the how behind the technology.
Because if you don't understand how a system works on a physical or molecular level, you won't understand how it fails.
And they absolutely do fail if you apply them improperly. So let's start at the absolute foundation. To build a machine that detects a fire, we first have to define what a fire actually is.
Right, which goes back to basics. Most people grow up learning about the fire triangle.
Yeah, the classic oxygen, fuel, and heat.
Exactly. And that is a totally fine model for, a middle school science class.
Yeah.
But in safety engineering, we use a much more precise model. We call it the fire tetrahedron.
A tetrahedron, so 4 sides.
Yes. The tetrahedron takes those 3 base elements, the oxygen, fuel, and heat, and it adds a 4th absolutely critical component.
Which is the self-sustained chemical chain reaction.
Spot on. That chain reaction piece is just fascinating. Because just having a pile of dried timber, plenty of atmospheric oxygen, and a lit match that isn't enough on its own.
Right, the combustion process actually has to cross a specific threshold, right?
Yeah, it has to be in feeding itself.
Yeah.
The heat radiating from the burning fuel has to be sufficient to vaporize adjacent unburned fuel.
Mixing it with the oxygen and igniting it in this continuous loop.
Exactly. And when that loop is finally established, the fire essentially becomes an autonomous entity.
It's alive, basically.
Pretty much. And to suppress that fire, the physics dictate that you have to forcibly remove at least one of those 4 elements.
So you could starve it by removing the fuel.
Right. Or you could smother it with a foam blanket to separate the fuel from the oxygen.
Or dump massive amounts of water on it to just absorb all that thermal energy and kill the heat.
Yeah. Or you can even introduce specialized chemical agents, like clean agent gases. Those actually interrupt the combustion chain reaction at a molecular level.
But, and this is a massive but, there is a logical hurdle before any of that suppression can even happen.
You have to know it's there.
Exactly. Before a sprinkler head pops, or a foam deluge system activates, or, a fire brigade gears up the facility, has to realize it's actually under attack.
That is the critical gap that fire detection systems fill. A modern facility is essentially a living organism.
I love that analogy.
Yeah, and the fire detection network is its central nervous system. It provides the sensory input.
Because when we're talking about fire development, time is it's the ultimate currency.
Oh, absolutely. Fire grows exponentially. A delay of 2 minutes in detection doesn't mean the fire is twice as big.
It might be 8 or 16 times as big.
Right. If you fail to detect the anomaly in its incipient stage, your suppression systems, your evacuation plans, your first responders, they are all already operating at a severe, potentially fatal deficit.
So let's follow the logic of that fire tetrahedron to explore our first category of detection. If one of the primary pillars of a fire is heat, it makes perfect sense that measuring thermal energy was historically the first approach engineers took.
Yeah, trying to build automated alarms based on temperature. And measuring heat is really straightforward in a controlled lab setting.
Sure, with no drafts and perfect conditions.
Exactly. But a commercial or industrial facility is the exact opposite of a controlled environment.
Totally. The engineering challenges become glaringly apparent the minute you try to put a thermal sensor in the real world.
Yeah, because if you just tell an electrical engineer, hey, build a device that closes a circuit when it feels hot, you immediately hit a brick wall of environmental variables.
Because a building breathes, the ambient temperature fluctuates wildly.
Right. You have massive HVAC systems kicking on, blowing warm air around.
Or bay doors rolling open and letting all that heavy summer heat in.
Or even manufacturing equipment. Think about injection molding machines or industrial ovens. They radiate immense thermal energy just by doing their normal jobs.
Right. So the central dilemma for the engineer is figuring out how to detect a legitimate, life-threatening fire without triggering a facility-wide evacuation every single time the sun comes out.
Or every time someone opens an oven door.
Exactly. Which brings us to the most basic tool in the arsenal, the fixed temperature heat detector.
The old reliable.
Yeah, and these come in a few forms, right? You have your spot detectors, which look like little metal discs on the ceiling meant to protect a localized area.
Right, and you also have line detectors. Those look like a continuous cable run along a ceiling or sometimes woven through a cable tray.
But regardless of what they look like, they operate on a strictly binary premise.
Yes, they trigger an alarm only when the ambient temperature of the air immediately surrounding them crosses a very specific, predetermined physical threshold.
The mechanics behind this are usually quite simple, aren't they?
Very simple and highly reliable. Many of them use a bimetallic strip.
Okay, break that down for the ASP candidates. What is a bimetallic strip?
So it's a small strip composed of two different types of metal that are welded together. And because different metals expand at different rates when they're exposed to heat, something interesting happens.
As the temperature rises, one side expands faster than the other.
Exactly. And that unequal expansion forces the strip to physically bend.
And when it bends far enough, it just touches an electrical contact, closes the circuit, and boom, the fire panel goes into alarm mode.
That's it. Or alternately, they might use a fusible alloy.
Like a piece of solder.
Right, a piece of solder specifically formulated to melt and break at exactly 135 degrees Fahrenheit, or maybe 200 degrees, depending on what rating you buy.
So their reliability is their greatest strength. They're simple physical mechanisms, but that's also their greatest weakness.
Massively. Let's look at a scenario from the source materials that highlights a really common pitfall that safety professionals have to avoid.
Okay, lay it on me.
Imagine a sprawling, single-story warehouse with an uninsulated corrugated steel roof. And let's say it's located in a hot climate, like the middle of the Texas desert in August.
Oh man, the sun is just baking that metal roof for 14 hours a day. The radiant heat transfer into that building is going to be massive.
Exactly. So if an inexperienced designer installs a standard 135-degree fixed temperature spot detector right up against the steel beams of that roof, they have just engineered a failure.
Because the ambient air pocket trapped against that ceiling on a summer afternoon is easily going to reach 135 or 140 degrees just from the sun alone.
Yeah, you've basically installed a smoke detector right above your kitchen stove.
That's a perfect analogy.
Okay.
It isn't a life safety device anymore. It's just an evacuation machine triggered by the weather.
And the consequence of that design flaw is really severe, because the first time that alarm sounds, the fire department rolls out, all the workers evacuate, and production completely stops.
Losing thousands of dollars.
Right. The second time, people grumble. But by the fifth time that alarm goes off in a single week, just because of the afternoon sun.
The workers will just stop evacuating. They'll assume it's another false alarm.
Exactly. That is the cry-wolf effect, or alarm fatigue. And in safety engineering, you have to understand that complacency is just as dangerous as the fire itself.
If people stop believing the sensory organs of the building, the whole safety ecosystem collapses.
Which is exactly why the implementation of a fixed temperature detector is never a guess. It requires a really rigorous engineering survey of the facility.
The safety professional has to determine the absolute maximum normal ambient temperature of that specific microenvironment, right?
Yes. The ceiling peak, the area near the boiler, the space above a production line. You have to establish a definitive worst-case scenario baseline.
Before you can select a device with a threshold that sits appropriately above that baseline.
Exactly. But even if you perfectly calculate the baseline, say you install a detector rated for 190 degrees in that hot warehouse, you are still relying purely on a fixed number. And that creates a terrifying vulnerability regarding the actual speed of a fire.
Because if a fire starts in a pile of highly combustible wooden pallets, it might be growing violently, doubling in size every minute.
Right, but if the warehouse has a 50-foot ceiling and massive air conditioning units running, the actual air temperature at the ceiling might take 10 full minutes to reach that 190-degree fixed threshold.
And 10 minutes in a fire is an absolute eternity.
It's game over. By the time that fixed temperature switch finally bends and makes contact, the fire below is a towering inferno.
Completely beyond the control of portable extinguishers, maybe even overwhelming the sprinkler system.
Right. The fixed temperature detector successfully answered the question, is it hot? But it totally failed to answer the much more important question, how fast is it getting hot?
Which means we need a piece of technology that completely ignores normal, slow temperature fluctuations, like the sun coming up, but instantly recognizes an unnatural, aggressive spike in thermal energy.
And that specific requirement led to the development of the rate of rise heat detector.
Rate of rise. Okay, I love this one.
It is a masterclass in pneumatic engineering. It solves the ambient temperature problem by measuring the velocity of the temperature change.
And there's a specific metric here for the exams, isn't there?
Yes, candidates need to know this. The typical threshold for a rate of rise detector is an ambient temperature increase of 12 degrees Fahrenheit, or roughly 6.7 degrees Celsius per minute.
12 degrees per minute. Let's spend some time on how this actually works mechanically, because it is brilliant.
It really is.
We aren't talking about modern digital microprocessors running algorithms to calculate the slope of a temperature curve. These devices have been around for decades.
Yeah, they rely on simple fluid dynamics and pressure. The internal architecture is elegantly simple.
Walk us through it. What's inside the casing?
Okay, inside the detector housing, there's a small, sealed pneumatic chamber filled with air. And the bottom of this chamber is a flexible metal diaphragm.
And just below that diaphragm sits an electrical switch connected to the fire alarm panel.
Exactly. So here is the physics at play. When the air in the room heats up, the air inside that sealed chamber also heats up. And as gases heat up, they expand.
Which creates pressure.
Right. And that pressure pushes down on the flexible diaphragm. If the diaphragm pushes down far enough, it clicks the electrical switch and triggers the alarm.
But wait, if that was the entire mechanism, it would just act like a really convoluted fixed temperature detector based on barometric pressure.
Exactly. That's the catch. The genius of the rate of rise design lies in a secondary feature. It's a microscopic, meticulously calibrated opening called a bleed hole.
The bleed hole, this changes everything. It's literally a tiny leak intentionally built into the air chamber.
Yes. So when the temperature in the room rises slowly, like the building's heating system kicking on in the morning and raising the temp at maybe 1 degree per minute, the air inside the chamber expands slowly too.
And because the expansion is slow, the excess pressure just easily escapes through that tiny bleed hole.
Exactly. The pressure inside the chamber equalizes with the outside air. It means the flexible diaphragm never actually gets pushed down.
I like to think of it like trying to fill a bucket that has a hole drilled in the bottom.
That's a perfect way to visualize it.
If you pour water into the bucket from a slow, trickling garden hose, the water just drains right out the bottom. The bucket never fills up.
Right, and that slow trickle of water represents the slow, normal rise of ambient heat in a building.
But when a fire breaks out, the thermodynamics change completely.
A rapidly growing fire sends a massive, sudden plume of thermal energy to the ceiling. The temperature spikes aggressively, way past that 12 degree per minute threshold.
So the air inside the detector's chamber heats up instantly and expands violently.
And that expansion happens so fast that the tiny bleed hole is just completely overwarmed. It cannot vent the air quickly enough.
So the pressure inside the chamber skyrockets.
Yep, forcing the metal diaphragm downward.
Yeah.
It strikes the contact, closes the circuit, and the fire panel goes into full alarm.
Going back to the bucket analogy, it's like taking a 50-gallon barrel of water and dumping it into the bucket all at once.
The hole in the bottom is still there, but it just can't handle that massive sudden volume.
The bucket fills up instantly and overflows. And that overflow is your fire alarm triggering.
The mechanical interplay between the expanding air and the restricted vent is literally a physical calculation of the rate of temperature rise.
It's incredibly clever, and it completely immunizes the system against the slow baking of the summer sun.
It does. But, like all engineering solutions, the rate of rise detector has its own specific vulnerability.
Of course it does.
Because it relies entirely on a rapid increase in heat, it is dangerously blind to slow-developing smoldering fires.
Oh, wow. Yeah, that is a terrifying scenario. Imagine a fire that starts inside a massive, densely packed bale of recycled paper or cotton in a warehouse.
It doesn't burst into bright hot flames. It just smolders. It slowly burns its way outward over the course of several hours,
Generating massive amounts of lethal smoke and carbon monoxide, but the actual heat release rate is very low.
Right. So in that scenario, the temperature at the ceiling might be steadily climbing, but it's only climbing at a rate of, say, 4 or 5 degrees per minute.
Which is well below the 12 degree per minute threshold.
Exactly. So the rate of rise detector just sits there. The air inside the chamber expands slowly, the bleed hole vents the pressure perfectly, and the diaphragm never moves.
The room could reach 150, 160, 200 degrees, filling with choking black smoke, and that detector will remain completely silent.
Which is a massive problem.
So we have fixed temperature detectors that can be fooled by the weather. And we have rate of rise detectors that can be fooled by a slow, smoldering fire. If you are designing a system for a complex environment, how do you bridge that gap?
You utilize a specialized piece of hardware called a rate compensation detector.
Rate compensation?
Yes. And this device is frequently tested on the safety exams because candidates absolutely must clearly differentiate its mechanics and purpose from the standard rate of rise detector.
Let's break it down then. On paper, it sounds like a fixed temperature device because it responds to a specific preset temperature threshold, right? Like 135 degrees.
Right, but its physical construction is totally different. It is specifically engineered to defeat a phenomenon known in physics as thermal lag.
Thermal lag. This is a crucial concept. It refers to the delay in heat transfer between the surrounding air and the physical mass of the detector itself.
Right. When a room suddenly heats up to 135 degrees, a metal object hanging from the ceiling doesn't instantaneously become 135 degrees.
The thermal energy has to actually conduct from the air into the outer casing of the detector and into the internal sensing mechanisms.
Exactly. The detector has mass, and mass takes time to heat up.
It's like putting a cold cast iron skillet on a hot stove. The air around the stove is hot immediately, but it takes a few minutes for that thick iron handle to actually become hot to the touch.
Perfect example. And in a fire scenario, thermal lag can be deadly. Imagine a fast-growing fire. The hot gases hit the ceiling and the air temperature reaches your critical 135-degree threshold.
But because of thermal lag, the internal bimetallic strip inside your fixed temperature detector might only be sitting at 110 degrees.
Right, it hasn't absorbed enough energy yet.
So the fire just continues to grow. The room temperature rockets to 150, 160, 180 degrees.
And the detector is desperately absorbing heat, trying to catch up to the environment.
By the time the internal mass of the detector finally hits 135 degrees and triggers the alarm, the actual air temperature around it might be 200 degrees.
The fire is significantly larger, and you have lost precious minutes.
So how does the rate compensation detector solve this?
It anticipates the rapid increase. The physical design usually involves an outer metallic tube or shell and an internal metallic strut assembly that holds the electrical contacts.
Okay, an outer shell and an inner strut.
Right, and the outer shell is made of a metal that expands rapidly when exposed to heat, while the inner strut expands much more slowly.
I see. So if the temperature in the room rises very slowly, like just a few degrees an hour, both the outer shell and the inner strut absorb the heat at roughly the same pace?
Exactly. They expand together, and when the entire device finally reaches the preset 135 degrees, the expansion pulls the contacts together, and it alarms just like a normal fixed temperature device.
But here's the brilliant part. In a rapid fire, the hot air hits the detector aggressively.
Yes, the thin outer shell immediately absorbs that heat and expands rapidly.
But because the inner strut is insulated and has a higher thermal mass, it stays cool and doesn't expand right away.
Right. That differential expansion of the outer shell stretching out while the inner strut stays rigid physically forces the electrical contacts to close prematurely.
It essentially jumps the gun.
That's exactly it. The detector feels the massive influx of heat on its outer skin, recognizes that the air temperature is skyrocketing, and physically forces the alarm to trigger before its own internal core has even reached the threshold.
It compensates for its own thermal lag.
Yes, ensuring that the alarm goes off the exact millisecond the surrounding air hits 135 degrees, regardless of how fast the fire is growing.
Man, that is a phenomenal piece of mechanical engineering. It provides the stability of a fixed temperature threshold without the dangerous delay caused by a fast-moving fire.
It's really the best of both worlds for heat detection.
So for anyone taking the ASP or CSP, rate of rise is measuring the speed of the temperature change. Rate compensation is looking for a specific temperature, but it uses differential expansion to eliminate the delay of thermal lag.
Understanding those mechanics is vital for property protection. But as we transition into our next major category, we really have to confront a sobering reality about fire dynamics.
What's that?
If you're relying purely on heat detection, you're almost always prioritizing property over human life.
Wow, that is a stark assessment.
It is, but the science supports it entirely. The source materials are incredibly clear on this point. In the vast majority of lethal fires, deadly conditions exist long before there is any significant buildup of heat at the ceiling.
Because the silent killer is not the thermal energy.
No, it is the smoke.
Smoke is a complex, really toxic soup. It contains particulate matter that physically blinds occupants, making evacuation impossible.
It contains carbon monoxide, which binds to hemoglobin in your blood and causes rapid asphyxiation.
And it contains hydrogen cyanide and all sorts of other off-gas chemicals from modern synthetic materials.
Right. If your safety strategy relies on a heat detector, you are literally waiting for the fire to generate enough thermal energy to heat a piece of metal 20 feet in the air.
And by the time that happens, the lower levels of the room could be entirely banked out with zero visibility, highly toxic smoke.
The occupants are already trapped or unconscious. To protect life, we cannot wait for the heat.
We must detect the invisible and visible particles of combustion in the air.
Exactly. We must move into the realm of smoke detectors.
And there are two primary technologies dominating this field, right? Ionization and photoelectric.
Yes, and they approach the problem of catching smoke using completely different principles of physics. Let's begin with the fascinating, almost science fiction mechanics of the ionization smoke detector.
When you really look at the schematic of an ionization detector, it is wild to think these are installed in millions of homes and offices. We are intentionally placing a radioactive isotope in the ceiling of a child's bedroom or a corporate boardroom.
It sounds alarming to the layperson for sure, but it is an incredibly safe, minuscule application of nuclear physics.
Okay, so how does it work?
An ionization detector utilizes a microscopic amount of a radioactive element, almost universally americium-241, and this tiny speck of material is housed inside a vented sensing chamber.
And americium-241 is constantly decaying, which means it is constantly emitting radiation, specifically alpha particles.
Right. Now, alpha particles are relatively large and heavy on an atomic scale, meaning they can't penetrate far. A simple sheet of paper or human skin stops them completely.
But inside that tiny plastic sensing chamber, they are incredibly powerful.
Yes. As these alpha particles shoot through the air inside the chamber, they violently collide with the oxygen and nitrogen molecules in the air.
And these collisions knock electrons right off the air molecules. This process is called ionization.
You're taking neutral air and turning it into a mixture of positively charged ions and free electrons.
Because the air inside the chamber is now ionized, it has become electrically conductive.
Exactly. The detector is designed with two metal plates, or electrodes, inside the chamber, and a small voltage is applied across them.
So under normal, clean air conditions, the ionized air acts as a conductive pathway, allowing a very small, continuous, and steady electrical current to flow from one plate to the other.
Right. And I love the analogy you use for this.
Oh, the bridge analogy. Yeah, so think of that steady electrical current as a smooth, perfectly flowing stream of commuter traffic crossing a large suspension bridge.
The cars being the electrons.
Right, the cars are just moving effortlessly from one side to the other. The detector's internal circuitry is monitoring this traffic. As long as the cars are moving at a steady pace, the detector is happy. The system is quiet.
But then a fire breaks out. Combustion particle smoke begin to drift up into the ceiling and enter that vented sensing chamber.
Now, on a macroscopic scale, to our eyes, smoke seems wispy and light. But on an atomic scale, compared to an ionized oxygen molecule, A smoke particle is an absolute behemoth.
It's massive.
Yeah.
When these massive smoke particles enter the chamber, the charged ions and electrons are immediately attracted to them.
The ions attach themselves to the smoke particles.
But because the smoke particles are so massive and heavy, they barely move.
So going back to the bridge analogy, it's like a fleet of giant, slow-moving, wide-load semi-trucks suddenly merging onto our commuter bridge.
They take up all the lanes.
Exactly. The fast-moving cars, the electrons get stuck behind them or crash into them. The smooth flow of traffic is instantly destroyed.
In electrical terms, the smoke particles neutralize the ions and drastically increase the electrical resistance inside the chamber.
The steady flow of current plummets.
And the detector circuitry senses this sudden drop in electrical current, realizes the bridge is blocked, and instantly triggers the alarm.
It is a flawless application of physics. A drop in current equals an alarm.
But from a safety engineering perspective, understanding how it works is only half the battle. You have to know what it is best at detecting.
And the source material emphasizes that ionization detectors are exquisitely sensitive to very small particles of combustion.
Right, and very small particles are the hallmark of a specific type of fire. High-energy, open-flame fires.
Like if a trash can full of crumpled paper catches fire, or a highly combustible liquid like gasoline ignites.
It burns fast and hot. This rapid combustion consumes fuel aggressively and churns out massive quantities of these microscopic, often completely invisible particles.
So an ionization detector will catch a flaming paper fire almost instantly. The invisible particles flood the chamber, attach to the ions, kill the current, and the alarm screams.
It is incredibly fast. But the physics of the ionization chamber also create its most dangerous blind spot.
Because the system relies on the interaction between ions and massive quantities of tiny particles, it struggles significantly with fires that produce larger, heavier particles.
Yes. Specifically, it is relatively insensitive to slow, smoldering fires.
Let's visualize that hazard. A maintenance worker tosses a rag soaked in linseed oil into a dense canvas bin. Over hours, it begins to undergo spontaneous combustion.
It doesn't burst into flames, it just smolders intensely.
Or a frayed electrical wire inside a wall slowly scorches a wooden stud.
These smoldering fires do not produce the microscopic high-energy particles that trip an ionization chamber.
Instead, they produce large, heavy, cooler smoke particles, the thick, visible, choking gray smoke.
Right. And because there are fewer of these particles, and because they are so large, they don't efficiently interrupt the ion flow in the chamber.
The bridge traffic might slow down a tiny bit, but not enough to trigger the threshold.
A room could literally fill waist deep with deadly, opaque smoke from a smoldering couch cushion, and the ionization detector on the ceiling might just sit there, humming happily, completely blind to the lethal environment.
Which is terrifying for residential and commercial safety.
It is. However, from a logistical and financial standpoint, ionization detectors are incredibly attractive to builders and facility managers.
Because they're cheap and easy to install. The study materials highlight a key operational detail. Ionization detectors require extremely low amounts of power to maintain that tiny internal electrical current.
They can operate on standard low-voltage batteries.
You can go to any hardware store, spend $15, and walk out with a battery-operated ionization detector. Screw it into the ceiling in 3 minutes. No wiring, no electricians.
Their versatility is unmatched. They're used for localized spot detection in offices, and they're frequently installed inside the ductwork of HVAC systems to monitor the air being circulated throughout a massive building.
But because of their vulnerability to smoldering fires, the safety professional must look to the second major category of smoke detection to ensure comprehensive life safety.
We have to move away from electricity and radioactive isotopes and move toward the physics of light.
Photoelectric smoke detectors.
Exactly. While ionization detects the invisible particulate of a fast fire, photoelectric detectors are designed to respond to both the visible and invisible products of combustion.
And their crowning achievement is that they are highly sensitive to the thick, heavy smoke produced by those slow, smoldering fires.
They fill the exact gap left by the ionization detectors. If you have a hazard profile that suggests a high risk of smoldering fires, perhaps a furniture warehouse, a textile plant, or a facility with massive amounts of dense, combustible storage photoelectric, is the mandatory engineering choice.
But there is a massive logistical trade-off here, and candidates absolutely must catch this in the study guides.
What's the trade-off?
Because photoelectric detectors actively project a beam of light to search for smoke, they consume significantly more power than an ionization chamber.
Yes. The source material is explicit on this operational limitation. Photoelectric detectors need a relatively powerful, continuous supply of electricity.
Historically, and in many industrial applications, they cannot be reliably operated by standard batteries. They must be hardwired into the building's electrical grid.
Which fundamentally shifts the safety professional's role from a simple equipment selector to a major project manager.
Think about the real-world implications of this. If you're designing a brand new, modern office tower, hardwiring 100 photoelectric detectors into the ceiling is just a line item on the electrical blueprint. The electricians run the conduit before the drywall goes up. It's easy.
But safety professionals rarely spend their entire careers in brand new buildings. You are often tasked with auditing and retrofitting existing structures.
Right. Imagine you are hired to upgrade the fire safety systems of a 100-year-old historic hotel.
Oh, that's a nightmare scenario for retrofit.
It is. The hazard analysis shows a huge risk of smoldering fires due to the antique furniture, heavy drapes, thick carpeting. You know you need photoelectric detectors.
But you can't just stick battery-powered units to the ceiling.
Exactly. You now have to hardwire every single room. You are pulling thousands of feet of conduit.
Yeah.
You are tearing into century-old lath and plaster walls.
You might have to upgrade the main electrical breaker panels for the entire floor to handle the dedicated fire alarm circuits.
And you have to coordinate with historic preservation societies to ensure you aren't destroying the aesthetics. What started as a straightforward safety upgrade has exploded into a multi-million-dollar capital construction project.
This is why mastering this material isn't just about passing the CSP. It's about understanding how the physics of a light bulb in a plastic casing can dictate the budget and operational downtime of an entire corporation.
Absolutely. The physical demands of the technology dictate the installation logistics.
So to fully grasp why they require this power, we need to examine the internal engineering. The texts delineate 3 distinct operating principles used in photoelectric detectors.
Let's explore the optical engineering. The first, and perhaps most intuitive design, is based on light obscuration.
Light obscuration is elegant in its simplicity. Inside the detector sensing chamber, there is a small light-emitting diode, an LED acting as the light source.
And it projects a steady, focused beam of light across the dark chamber.
Right. Directly across from the LED, in the path of the beam, is a photosensitive receiver, a sensor that reads light intensity.
It's a closed loop. The LED shines the light, the receiver catches the light. As long as the receiver is registering 100% of the light intensity, the system knows the air in the chamber is clean.
Well, when a smoldering fire begins, those large, heavy smoke particles drift into the chamber. As they pass between the LED and the receiver, they physically block the light.
The smoke obscures the beam. It operates exactly like the laser tripwire of a security system in a bank vault.
Yes. When the jewel thief breaks the laser, the alarm goes off.
In this case, the thief is a cloud of thick smoke. As the smoke gets denser, less and less light reaches the receiver. Once the light intensity drops below a specific engineered threshold, the internal circuitry tricks the alarm.
It is incredibly effective for thick smoke. But engineers also developed a secondary method that uses the light in the opposite manner.
The light scattering principle.
Exactly. In the obscuration model, the sensor is looking directly at the flashlight. In the light scattering model, the architecture is subtly shifted.
You still have an LED projecting a beam of light across a dark sensing chamber.
Yes. However, the photosensitive receiver is moved. It is placed off to the side, outside the direct path of the light beam.
And it's positioned behind a physical baffle.
Right. Under normal, clean air conditions, the beam of light shoots straight across the chamber and hits a light-absorbing black wall. The receiver sits in complete darkness.
Because the receiver's in the dark, it tells the fire panel everything is fine. So how does it detect the smoke if the beam isn't even pointed at it?
It relies on the reflective properties of particulate matter. When smoke from a fire enters the chamber, those large particles intersect the beam of light.
And instead of just blocking the light, the physical surface of the smoke particles acts like millions of microscopic, faceted mirrors.
They strike the beam and reflect it. The light hits the smoke and scatters chaotically in every possible direction.
Because the light is bouncing everywhere, some of that scattered light makes its way around the baffle and strikes the photosensitive receiver that was previously sitting in the dark.
The receiver suddenly detects light where there should be none. Once the amount of scattered light hitting the sensor reaches a critical level, it triggers the alarm.
The best analogy for this is driving your car down a dark country road on a foggy night.
Oh, that's a good one.
Right. So if the air is clear and you turn on your high beams, the light shoots straight ahead, illuminating the road. But if you hit a thick patch of fog, what happens when you hit the high beams?
The light hits the microscopic water droplets suspended in the air.
Exactly, and it scatters. It reflects off the water and bounces right back into your eyes, completely blinding you with a wall of white light.
The light-scattering photoelectric detector is intentionally utilizing that exact phenomenon. The LED is the high beam, the smoke particles are the fog, and the receiver is your eye getting hit with the reflected glare.
It uses the physical mass of the smoke to bend the light toward the sensor.
Both obscuration and scattering rely on optical manipulation. But the third principle, detailed in the source material, the cloud chamber principle, steps away from simple optics.
It ventures into complex atmospheric physics and thermodynamics. When I first read about cloud chamber detectors, I was astounded.
It's next-level engineering.
This isn't just a passive sensor waiting for smoke to drift into a plastic shell. This is a dynamic, mechanical machine actively hunting for microscopic signs of combustion.
Yes. A cloud chamber detector acts almost like an artificial lung. It utilizes a mechanical aspirator or pump to actively draw a continuous sample of air from the protected space into a highly specialized, sealed internal chamber.
And once that air sample is trapped inside, the detector alters the environment completely. It introduces moisture, artificially raising the humidity inside the chamber to a near saturated level, basically 100% relative humidity.
So the air is damp and heavy, but it is still technically clear. The genius step happens next.
The mechanical system rapidly, but slightly, lowers the barometric pressure inside that humid chamber.
Why manipulate the pressure? We have to look at the physics of condensation.
Right. According to the principles of thermodynamics, when you rapidly drop the pressure of a gas, you also drop its temperature.
If you take air that is already at 100% humidity and suddenly drop the temperature, the air can no longer hold all that moisture. The water vapor is desperate to condense back into a liquid form.
But water vapor needs a nucleation site to condense upon. It needs a physical surface to cling to.
In clean air, this condensation is difficult. But if there are invisible sub-micron smoke particles present in that air sample, even in quantities far too small for an ionization or standard photoelectric detector to notice, those particles act as perfect nucleation sites.
The moisture violently condenses around millions of these microscopic smoke particles.
The physical result is that the detector literally generates a miniature, dense weather system inside the chamber. It forms a highly visible, opaque cloud.
Once this artificial cloud is formed, the system falls back on optical physics. A photoelectric beam shines through the chamber.
If the system successfully created a cloud, meaning smoke was present in the air sample, to act as the seed, the cloud obscures or scatters the light, and the alarm is triggered.
It is an astonishingly complex process. Draw air, humidify, depressurize, condense, illuminate, analyze, purge, and repeat. And it does this continuously.
It's creating localized weather events to amplify the presence of invisible smoke.
It demonstrates the incredible lengths engineers will go to shave seconds off a detection time. But even with the brilliance of cloud chambers, rate compensation, and ionized particles, there are modern environments where standard ceiling-mounted detectors are simply inadequate.
Because standard detectors are passive. They sit in the ceiling and wait for the thermal plume of a fire to push the smoke up to them.
In 90% of commercial applications, offices, schools, retail stores, that is sufficient. The fire grows, the smoke rises, the alarm sounds, people evacuate.
But what if you were protecting a facility where the sheer concept of a fire growing is an unacceptable failure?
You were talking about high-value, high-consequence environment.
Exactly. Imagine a hyperscale data center, a massive server farm processing financial transactions for a global bank, or hosting the cloud infrastructure for a hospital system.
The room is filled with rows upon rows of server racks generating intense heat, cooled by massive, high-velocity air conditioning systems.
The environmental dynamics are hostile to traditional detection.
The high-velocity HVAC systems are pushing so much air that they dilute the smoke.
Right. A small fire, starting inside a server chassis, might produce a thin wisp of smoke, but the air conditioning instantly disperses it, blowing it across the room before it ever gathers enough density to rise to a ceiling-mounted smoke detector.
By the time a traditional detector on the ceiling registers the diluted smoke, an entire rack of servers could be melted slag.
The facility has lost millions of dollars in hardware, and more importantly, suffered catastrophic data loss and operational downtime.
In these environments, you cannot wait for the smoke to come to you. You have to aggressively go out and find it.
This necessitates the move to specialized detection, specifically air sampling detectors, commonly referred to as aspirating smoke detectors.
We saw a basic version of this with the cloud chamber, but modern high-hazard systems take this to an entirely different technological tier, utilizing xenon-based optical analysis.
Yes, xenon air sampling.
Let's build a xenon air sampling system in our hypothetical server farm. Instead of individual plastic detectors screwed into the ceiling, the safety engineer installs a vast network of small-diameter PVC piping.
These pipes are run everywhere, crisscrossing the ceiling, dropping down inside the server cabinets, and running underneath the raised flooring where the massive power cables sit.
At regular intervals along this pipe network, tiny sampling holes are drilled.
And at the center of the network is a highly powerful, centralized mechanical aspirator, a vacuum pump.
This pump runs 247, creating a continuous negative pressure that actively sucks air through all those tiny holes, down the pipes, and into the central detection unit.
The system is literally inhaling the room constantly. It doesn't wait for smoke to rise, it pulls the environment into itself.
Once that air reaches the central unit, it passes through sophisticated filters to remove normal environmental dust and dirt. Then it enters the laser chamber.
This is where the xenon technology comes in. The system utilizes intense xenon lamps.
And xenon lamps are capable of producing a highly intense, broad-spectrum light, often spanning from ultraviolet through the visible spectrum into infrared.
By passing this incredibly intense, pure light through the continuously flowing air sample, the internal optical sensors can perform microscopic analysis.
They aren't just looking for a shadow cast by thick smoke, they are analyzing the forward scattering of light at a particulate level.
The sensitivity is staggering. A xenon air sampling system can detect the microscopic off-gassing of plasticizer.
Which means if a power cable underneath the floorboard starts drawing too much current, the copper wire heats up.
Right. Long before the plastic insulation melts, long before it smolders, and hours before it produces visible smoke, it begins to release microscopic particles into the air.
The aspirating pipe sucks those particles up, the xenon laser hits them, the system registers the exact density and size of the particulate, and it triggers a pre-alarm.
The system alerts the facility manager. We have a microscopic increase in combustion particles in Zone 4.
The manager can just walk over, find the overheating wire, and power it down before a fire ever actually ignites.
Yeah, it is the crucial takeaway for the exam and for real-world engineering. The study materials explicitly state that xenon air sampling is considered the most reliable and valid measure of fire intensity.
It gives you a granular, real-time graph of exactly how much particulate is in the air. It is the absolute gold standard for clean rooms, telecommunications hubs, and server farms.
It provides the ultimate early warning. But there is another extreme end of the hazard spectrum.
Okay, what's that?
What if you are protecting an environment where smoke is completely irrelevant? What if you are designing safety systems for an outdoor petrochemical refinery or a munitions manufacturing plant?
Oh. In a petrochemical facility, if a high-pressure pipe carrying aviation fuel or compressed hydrogen ruptures and ignites, there is no smoldering phase.
None. There is no slowly building thermal plume. There is an instantaneous explosive fireball.
Furthermore, many of these volatile chemicals burn incredibly clean. A hydrogen fire, for example, produces almost zero visible smoke.
A smoke detector, even a xenon aspirating system, would be completely blind to it. And relying on a heat detector to trigger while a hydrogen fireball expands across a refinery deck is a recipe for catastrophe.
For these specialized high-velocity hazards, we have to bypass the physical byproducts of smoke and heat entirely. We have to detect the fire at the speed of light.
We use flame detectors.
Flame detectors are essentially highly specialized optical cameras, right?
Basically, yes. When a combustible material burns, the violent chemical chain reaction emits energy in the form of electromagnetic radiation.
We see the visible part of this spectrum as light, but a fire also pumps out massive amounts of invisible radiation in specific bands of the spectrum.
Specifically, ultraviolet UV radiation and infrared IR radiation. Flame detectors are equipped with sensors explicitly tuned to see these specific invisible wavelengths.
So a UV flame detector is looking for the short wavelength radiation emitted at the exact moment of ignition, the spark, and the initial flame.
And an IR detector is looking for the longer wavelength radiation, specifically the flickering frequency typical of a turbulent flame.
Because they're looking for light, they react instantly. The millisecond a methane valve ignites, the UV-IR detector sees the flash and triggers the deluge suppression system.
It is life-saving speed. But this incredible speed and optical sensitivity introduces one of the most frustrating dilemmas a safety professional will ever face.
The false alarm potential of flame detectors is legendary in the industry.
They're almost too good at their jobs. The sources mention that UV and IR detectors can be accidentally triggered by a staggering array of completely normal non-fire sources.
Let's consider the UV detector. It is searching for intense bursts of ultraviolet light. You know it produces massive amounts of UV light?
Arc welding.
Exactly. Imagine you have a massive automotive manufacturing floor. You install UV flame detectors to protect the paint booths from chemical fires.
Okay.
50 feet away, a maintenance contractor strikes an arc on a welding rig to repair a broken conveyor belt.
The UV flash from that welding arc bounces across the factory floor, hits the lens of the flame detector, and the system instantly assumes there's an explosive fire.
The alarms scream, the assembly line grinds to a halt, and perhaps thousands of gallons of fire retardant foam are dumped onto the paint line, ruining millions of dollars of product and causing days of downtime, all because of a welding spark.
And it isn't just welding. The flicker of a worker striking a cigarette lighter can trigger some sensitive IR detectors.
Sometimes, if the sun hits a puddle of water or a shiny piece of diamond plate steel at just the right angle, the intense reflected solar radiation can overload the sensor and trick it into alarming.
Facility managers absolutely despise false alarms that shut down production, so the immediate reactionary response is often to shield the detectors.
If the detector keeps getting blinded by the welding station on the other side of the factory, a technician might bolt a metal blinder or shield to the side of the detector casing so it can't see that direction anymore.
Which creates a terrifying paradox. The shielding stops the false alarms, making the facility manager happy, but you have just intentionally blinded your safety system.
If you put a physical blinder on a flame detector to block the glare from a window, that detector is now completely useless if an actual lethal fire breaks out in the shadow of that blinder. You have created a dead zone in your protection grid.
This is why the study guides and NFPA codes heavily emphasize that the selection, placement, and aiming of flame detectors cannot be left to guesswork or trial and error. It requires a rigorous, almost obsessive engineering survey.
The safety professional must map out the entire facility in 3 dimensions. They must plot every potential source of radiant energy, every window, every reflection point, every designated hot work area.
They must calculate the cone of vision for every single detector, ensuring overlapping coverage so that if one detector is blocked by a passing forklift, another can see the hazard.
They might have to utilize multi-spectrum detectors, which require both a UV and an IR signature to trigger simultaneously, mathematically reducing the chance of a false alarm.
It is a massive balancing act between the need for instant detection and the financial ruin of false alarms.
To round out our specialized category, the sources briefly touch upon gas sensors. In certain industrial applications, the primary hazard isn't the flame or the thermal energy, but the invisible, lethal gases produced before or during combustion.
These are highly specific devices calibrated to detect target gases like carbon monoxide, hydrogen sulfide, or unburned combustible gases like methane.
They utilize specialized electrical circuits, often catalytic bead sensors that physically burn a tiny sample of the gas to measure its combustibility.
Or electrochemical sensors that use a chemical reaction to generate a measurable electrical current when exposed to the target gas.
They are a vital layer of defense in chemical processing, mining, and confined space environments, ensuring workers aren't asphyxiated before a fire even ignites.
So let's take a breath and look at the vast arsenal we have explored.
We have rate of rise detectors doing pneumatic calculus. We have ionization chambers splitting atoms.
We have cloud chambers making weather, xenon lasers counting microscopic dust, and UV cameras staring at the speed of light.
The technological achievement is just staggering. But it brings us to a harsh systemic reality.
A $100,000 xenon air sampling system detecting the invisible off-gassing of a wire with perfect accuracy is completely, utterly useless if it just sits there humming quietly to itself while the building burns down.
Detection is merely the acquisition of data. That data must be transmitted, processed, and acted upon.
The individual, isolated sensors must integrate into a holistic, facility-wide safety nervous system.
This requires us to elevate our perspective from the individual device to the overarching architecture. And for our ASP and CSP candidates, this means stepping into the rigid, legally binding world of standard-setting bodies.
Welcome to the world of the National Fire Protection Association, specifically NFPA 72, and the Occupational Safety and Health Administration, OSHA.
NFPA 72 is the National Fire Alarm and Signaling Code. It is the definitive rulebook governing how these systems communicate.
When any detector senses an anomaly, it sends a signal via hardwire or secure radio frequency to the central fire alarm control panel.
The control panel is the brain. It sits in the electrical room or the security office, receiving thousands of data points a second from the sensory network.
But it doesn't treat all data equally. The panel must interpret what the signal means.
This is a vital concept for the exams. In the SPAN CSP Volume 1 quiz, there is specific emphasis placed on the classification of system signals.
Fire protection systems utilize 3 distinct types of signals: alarm, trouble, and supervisory.
Candidates absolutely must know the difference, because treating a trouble signal like an alarm or vice versa is a catastrophic failure of procedure.
Let's build distinct scenarios for each to make them memorable.
Okay, the alarm signal is the most critical and the most obvious.
This means a detector has unequivocally sensed a fire condition. The photoelectric beam has been obscured. The fixed temperature link has melted.
The panel registers the alarm signal, illuminates in red, and the facility goes to war. Evacuation horns sound, strobes flash, and the dispatch system automatically dials the municipal fire department.
A trouble signal is entirely different. An alarm means there's a fire. A trouble signal means the fire safety system itself is broken.
Imagine a forklift driver is moving a tall pallet in the warehouse and accidentally clips the metal conduit running along the ceiling, severing the communication wire to a cluster of rate-of-rise heat detectors.
The control panel instantly realizes it has lost communication with that zone. It registers a trouble signal, usually accompanied by a yellow light and a persistent, annoying buzzing sound at the panel.
It is the system's way of telling the safety manager, I am not detecting a fire, but I am currently blind in Zone B. You have a critical failure in your safety infrastructure, and you must repair the wiring immediately.
A trouble signal requires an immediate maintenance response, but it does not require an evacuation.
Then we have the third category, the supervisory signal. This one is nuanced.
A supervisory signal monitors the operational readiness of the system, or the status of interfaced equipment.
It indicates that the system is functioning normally, but a critical component has been moved from its normal state, usually by human action.
The classic example involves the automatic fire sprinkler system. A massive network of water pipes is useless if the main water valve is shut off.
These valves, often post-indicator valves in the yard or butterfly valves in the pump room, are equipped with tamper switches.
If a plumber comes in to do maintenance and closes the main water valve to the sprinkler system, the tamper switch activates.
The fire panel registers a supervisory signal. The panel is saying, I'm functioning, the wiring is fine, there is no fire. But someone has turned off the water. If a fire starts right now, the sprinklers will fail.
It is a warning that the operational readiness of the facility has been compromised.
The safety professional must investigate immediately, ensure the plumber finishes the work, and physically verify that the valve is locked back in the open position.
Understanding alarm, trouble, and supervisory signals allows the safety professional to manage the panel. But beyond the NFPA communication codes, we must strictly enforce OSHA regulations regarding the physical maintenance of the system.
OSHA has immense authority here, and their regulations are built on the blood and ashes of historic industrial tragedies. Let's look at the maintenance requirements from our sources.
First, detection systems must be installed in specific, documented, and labeled locations. You cannot just hide a smoke detector above a drop ceiling tile because it looks ugly, unless you have explicit signage indicating its location.
They must be installed correctly according to the manufacturer's engineering specifications. Improper installation, like putting a smoke detector too close to a high-velocity air return vent where the smoke will be blown away from it, is a massive citation risk and a lethal failure.
They must be tested regularly. You cannot install a multi-million-dollar xenon system, walk away, and assume it will work perfectly 10 years later. Smoke is introduced, circuits are tripped, bells are rung.
Furthermore, they must be cleaned regularly. This is a massive issue in industrial environments. Think back to our light-scattering photoelectric detector. It relies on a pristine optical chamber.
What happens if that detector is installed in a woodworking shop or a textile mill? Over 5 years, microscopic sawdust or lint gets sucked into the chamber.
It coats the LED lens, it coats the dark baffles. Eventually, the accumulated dust either scatters the light itself, causing endless false alarms, or it forms a thick blanket over the sensor, completely blinding it to actual smoke.
OSHA requires rigorous, documented cleaning schedules to prevent the environment from destroying the detector.
OSHA also explicitly states that these systems must be kept on when not being serviced. If you have a faulty heat detector causing false alarms, you cannot just reach up and unplug it or bypass the zone on the control panel so you can finish your production shift in peace.
Operating a facility with a bypassed safety system is a direct, willful violation of safety law.
And finally, when an alarm does sound, the auditory signal must be distinct and unique.
It has to cut through the cognitive overload of an industrial environment. If a worker hears a buzzer, they shouldn't have to wonder, is that the fire alarm, or is it the crane moving, or is it the shift change whistle?
The temporal 3-pattern beep, beep, beep pause must unequivocally mean drop your tools and evacuate.
But the true marvel of a modern integrated fire system is that it doesn't just make a loud noise and wait for the humans to act.
When the central panel receives an alarm signal, it transforms into an automated incident commander, executing a complex sequence of life-saving actions in milliseconds.
The panel actively interfaces with the building's infrastructure. If a smoke detector trips in a secure laboratory, the panel instantly sends a signal to the access control system.
It drops power to all the magnetic locks on the doors, ensuring that fleeing employees aren't trapped by a security badge reader that melted in the heat. It ensures a free, unimpeded path of egress.
It looks upward to the roof. The panel can trigger automated fire and smoke hatches, blowing them open to vent the toxic superheated gases out of the building, preventing the smoke from banking down to the floor and asphyxiating the occupants.
It takes absolute control of the HVAC equipment. Depending on the engineering design, it might shut down the massive air handlers completely so they stop pumping fresh oxygen into the fire room.
Or it might do something much smarter. It might reverse the fans in the stairwells, pumping fresh outside air into the stairs to create positive pressure.
That positive pressure turns the stairwell into an invisible fortress. When fleeing employees open the door to the stairwell, the high-pressure clean air rushes out into the burning hallway, physically preventing the toxic smoke from entering the escape route.
The panel also captures the elevators. It initiates Phase 1 recall, instantly overriding any buttons pressed by occupants, bringing all elevator cars to the ground floor, opening the doors and locking them out of service.
This prevents terrified people from piling into a metal box and accidentally riding it into a floor fully engulfed in flames.
And crucially, the detection system is the absolute master of the automated fire suppression systems. A brilliant example detailed in the text is the deluge system.
Deluge systems are awe-inspiring to watch in action. They are the nuclear option of fire suppression. Normally, we think of a wet pipe sprinkler system, where each sprinkler head is independent.
The room gets hot, the little glass bulb on one specific sprinkler head shatters, and water comes out only over the fire.
But in a deluge system designed for extreme hazards, you don't have the luxury of waiting for individual heads to heat up. In a deluge system, the heat sensors, the glass bulbs, or fusible links have been intentionally removed from every single sprinkler head during installation.
The pipes are completely open to the room, gaping maws pointing at the floor, but they are completely dry. There is no water in the ceiling pipes.
The thousands of gallons of water or chemical foam are held back in a mechanical room by a massive mechanized central valve, the deluge valve.
So what tells that massive valve to open? The fire detection system.
Exactly. Imagine a military aircraft hangar. You have a multi-million-dollar fighter jet sitting on the deck surrounded by mechanics, and there are thousands of gallons of highly explosive aviation fuel in the tanks.
If a fuel line ruptures and ignites, a standard sprinkler system is useless. The fire will spread across the floor instantly.
But the hangar is equipped with a matrix of UV and IR flame detectors. The millisecond the fuel ignites, the flame detectors see the radiant energy.
They send the alarm signal to the central panel. The panel bypasses all the HVAC and door locks and sends an immediate electrical pulse to the deluge valve in the pump room.
The deluge valve violently opens. Massive industrial pumps kick in. The water and foam rush into the dry pipe network.
Because all the sprinkler heads are already open, the water pours out of every single head in the entire hangar simultaneously.
Within 30 seconds, the entire hangar floor, thousands of square feet, is buried under 3 feet of fire-retardant foam. The fire is drowned instantly.
And that entire massive mechanical response was initiated because a small optical sensor on the wall recognized the invisible wavelength of a flame. It is a breathtaking synergy of electrical, optical, and mechanical engineering.
It is the pinnacle of automated safety. But, and this is how we must conclude this extensive analysis, after all the xenon lasers, the pneumatic rate of rise chambers, the pressurized cloud systems, and the massive deluge valves, what is the ultimate fail-safe?
What happens when the power grid fails, the backup generators flood, and the technology breaks?
The final layer of protection is, and always will be, the human element. Because certain highly hazardous industrial operations are so chaotic and the fire potential is so immediate that you simply cannot rely on automated sensors to save lives.
This brings us to the human equivalent of a fire detection system, the fire watcher. The study guides highlight this role heavily.
When a facility is engaging in hot work, which includes major operations like welding, cutting, brazing, or heavy grinding, in an area that is not specifically designed for it, the standard automated fire precautions are considered legally and practically insufficient.
The safety professional must strip away the reliance on technology and assign dedicated, highly trained personnel to act as human sensors. The fire watcher's sole, exclusive job is to stand guard over the hot work area.
They cannot be checking their phone, they cannot be helping the welder hold the steel, they cannot be sweeping the floor, they watch.
They must be deeply trained to understand fire behavior. They must know the exact combustible loads in their area.
They must be equipped with and expertly trained on the specific firefighting equipment required for the hazard, whether that is a massive wheeled chemical extinguisher or a charged fire hose.
But here's the detail that catches candidates off guard on the exam and catches facility managers off guard in reality.
Ugh.
The fire watcher's job does not end when the welding torch is turned off.
The sources are emphatic on this point. The fire watcher must guard the operation area during the work and for a specified mandatory period after the operation is fully completed. Depending on the hazard, this can be 30 minutes, an hour, or more.
Why? Because of the terrifying physics of hot slag and sparks. Let's paint the scenario. A pipe fitter is cutting a thick steel pipe with an oxyacetylene torch near the ceiling of a warehouse.
A tiny molten globe of steel, a spark shoots off. It bounces off a girder, falls 20 feet, and rolls under a baseboard, landing in a hidden pile of combustible cardboard dust.
The welder finishes the cut. They turn off the torch, pack up their heavy gear, and head to the break room for lunch. They assume the job is done and the area is safe.
But that tiny piece of slag is sitting in the dust. It is intensely hot, but it lacks the oxygen to burst into flames immediately, so it smolders.
It burns invisibly, eating into the dust, growing hotter, generating a tiny thermal mass. It could sit there for 45 minutes completely hidden.
If the fire watcher leaves with the welder, that smoldering spark will eventually gain enough energy, find a pocket of air, and violently ignite into a flaming fire long after the area is deserted.
The fire watcher is the human equivalent of the rate compensation detector. They stay behind to monitor the thermal lag of the environment. They watch for the smoke that the automated systems might miss.
It is the ultimate heavy responsibility of the safety professional to ensure that this entire ecosystem, the technology and the humans, works in perfect, flawless synchronization.
You're the architect of the facility's survival. You have to ensure the ionization detector catches the fast-flaming fire in the trash can. You have to ensure the photoelectric detector catches the smoldering couch.
You have to ensure the xenon system protects the servers. The NFPA 72 panel routes the signals correctly. The deluge valve opens without hesitation. The stairwells pressurize, and the human fire brigade and fire watchers are rigorously trained and alert.
It is a staggering amount of technical knowledge and logistical oversight, which is precisely why this topic commands such a massive, uncompromising portion of the professional certification exams.
We have covered an immense landscape of engineering today. As we wrap up this session of QHSE Talks, let's consolidate the absolute crucial concepts you must internalize.
Regarding heat detectors, understand the mechanical difference between a rate of rise detector using expanding air and a bleed hole to measure the speed of temperature change, typically 12 degrees a minute, and a rate compensation detector, which uses differential metal expansion to anticipate thermal lag and trigger exactly at a preset temperature.
Regarding smoke detection, remember the physics. Ionization detectors use a tiny radioactive source to detect the microscopic, invisible particles of fast, flaming fires and offer the flexibility of battery operation.
Photoelectric detectors utilize light beams via obscuration, scattering, or pressure-induced cloud chambers to detect the heavy, visible smoke of slow, smoldering fires, but they demand the massive logistical hurdle of hardwired electrical power.
For specialized environments, xenon air sampling is the unquestioned gold standard for reliable early warning, actively inhaling the room to detect microscopic off-gassing.
Flame detectors look for the speed of light radiant energy of UV and IR wavelengths, but their extreme sensitivity makes them highly susceptible to false alarms from welding or sunlight, forcing safety professionals into the dangerous paradox of physical shielding.
And finally, at the systems level, you must master the NFPA 72 communication signals, the life safety urgency of an alarm, the maintenance demand of a trouble signal, and the operational warning of a supervisory signal.
You must enforce OSHA's strict demands for regular testing, cleaning, and unbypassed operation. And you must understand how these electrical signals translate to physical survival, from triggering dry pipe deluge systems to relying on the trained eyes of a human fire watcher during hot work.
That encompasses the core knowledge of ASP Domain 4, Topic 6. But before we sign off, we always like to push the boundaries of the curriculum.
We want to leave you with a provocative thought that builds on everything we've explored and challenges you to anticipate the future of safety engineering.
We spent this entire session of QHSE Talks detailing how we utilize mechanical expansion, radioactive isotopes, and optical beams to detect the physical byproducts of combustion: the heat, the smoke, and the radiant light.
But as our global infrastructure becomes increasingly reliant on artificial intelligence and predictive algorithms, how will the rigidly defined role of the safety professional shift?
Imagine a facility in the very near future where you don't install plastic detectors on the ceiling at all. Instead, an AI system taps directly into the warehouse's existing high-definition security camera network.
It doesn't wait for smoke to obscure a lens. It uses advanced pixel-level algorithms to detect the microscopic visual distortion of heat waves, the Schlieren effect rising off a failing conveyor belt motor.
It identifies the thermal signature of a fire mathematically, predicting the ignition seconds before smoke or ceiling heat ever physically exists.
It is an incredible technological leap, but it raises a massive bureaucratic question. How will standard-setting bodies like the NFPA and OSHA organizations, whose codes are deeply entrenched in the physical hardware of spacing, wiring, and testing, adapt to regulate software-based predictive AI detection?
How do you test the calibration of a learning algorithm?
It is a daunting frontier. It challenges you to think not just about the static regulations you must memorize to pass the exams today, but the complex, rapidly evolving landscape of software engineering and life safety you will be managing tomorrow.
You are entering a field where physics, chemistry, human psychology, and cutting-edge technology collide. Thank you for joining this extensive session of QHSE Talks. Keep studying the mechanics, keep questioning the standards, and above all, keep your workplaces safe.